So our second invited speaker is Mira Mezini. Thank you very much, Mira, for being here. Professor Mira Mezini is a full professor of computer science at Technical University of Darmstadt, where she leads the Software Technology Lab at the Department of Computer Science. She is known for her research on programming languages, intelligent software development environments, modular software architectures, and software security. She obtained her master's from University of Tirana in Albania in 1989 and her PhD in 1997 from University of Siegen in Germany. She was assistant professor at Northeastern University in the US before becoming associate professor of computer science at Technical University of Darmstadt in 2000, and then full professor in 2002. She was vice president of TU Darmstadt from 2014 to 2019, and currently she's a board member of Atine, if I remember it correctly, one of the 3 national research centers for IT security in Germany and one of the largest in Europe. And she's also the co-director of the new established Haitian Center for Artificial Intelligence. In 2016, she became member of the German Academy of Science and Engineering. In 2005 and 2006, Mira received the IBM Eclipse Innovation Award and a Google Research Award in 2018. In 2012, she received the ERC Advanced Grant, the European Union's highest endowed grant for programming abstractions for applications in cloud environments, PACE, and also an ERC Proof of Concept grant in 2019. This ERC Advanced Grants, this is #1, so this is very prestigious. Thank you very much, Mira, for accepting our invitation and for being here. We look forward to hearing your talk.
Okay, thank you very much, Marjan, for your very kind introduction, and thank you for having me here, for inviting me. Unfortunately, it ended up being only online. I would have loved to use this opportunity to visit Tehran and Iran, but yeah, we all know how it surprised all of us. Let me start by giving a quick summary of my talk so that you get a bit more information than what is possible by the title and can decide for yourself whether you want to stay or leave. So in the first part, the talk will be organized in 2 parts. In the first part, which I call here problem space, I will argue that computing has gone big and out of control and consensus is necessary but challenging. And in the second part, and in the middle, so at the end of the first part, I very briefly overview the solution space, emphasizing that language-based solutions are needed. And in the second part of the talk, I will present one specific language-based approach, Rescala, a programming language for consistent by design interactive distributed applications, which we have been developing in my team since several years. So this was also kind of the topic, or what I'm presenting is kind of result of the ERC Advanced Grant and the POC that followed after the ERC Advanced Grant. Okay, so I'm saying computing has become big and out of control. That means there was some time, some point in time where it was orderly and simple, and basically this is when computing started. We had, thanks to Alan Turing, we had universal machines that can execute any algorithm that we can write. And thanks to von Neumann, we had an architecture that realizes the Turing's theoretical model. The architecture is pretty simple and kind of ordered. It means we have a list of instructions, and state is also organized as an array, and then the execution model goes through the list of instructions with the program pointer, program counter, and executes them in the order in which they appear, thereby communicating via mutable state stored in memory. So these machines were universal as long as they don't break, but eventually machines break either by themselves or by some accident. And so we pretty soon lost this simplicity and universality, as also Rashid Geraoui puts in his recent Popple keynote in 2012. When the computing went big. So in order to ensure universality in face of failures, we had to replicate computations across connected computers. Basically, when ARPANET was born and basically the internet was born, so he coined this the infinitely big. This was great for failure tolerance, but paradoxically, with this move, other problems emerged with universality, because problems that were solvable before became unsolvable now unless we used consensus, which in theory, in the most general case, is impossible to solve, but under certain pretty much realistic assumptions, it can be solved, and it has been solved, but it's still challenging, as we will consider in a minute. And basically, as Rashid puts in his talk also, the problem is the same when we go infinitely small, kind of use the same processor via several threads or processes, or with the current state where we have several cores within the same machine going infinitely small, we have basically the same problems that we need to get consensus between different threads and between different processors. Now, compared to the 80s, today's computing has become even more or even bigger, and I would say also much more out of control. Let me explain what I mean. So what Geraoui called going big for increasing robustness and scalability represents actually the scenario of a rather well-organized setting of distributed clouds and distributed clusters under the control of distributed systems experts at tech companies. Today's internet machine, if you want, or internet machines, consists of millions of devices connected to each other and connected to the web, mobile, and cloud platforms via programmable networks. Devices in the network can themselves serve as clouds or can execute computations there. And this new computing, internet scale computing, runs massively and geo-distributed applications, such as social applications, instant messengers, multiplayer games, collaborative workflows like Google Docs and Figma and Trello, etc., real-time businesses, cross-organizational workflows, collaborative condition monitoring, and decentralized data ecosystems processing data owned by different stakeholders, and even more. So these machines, these applications are not only big and massively distributed, they are kind of out of control. And what I mean by this are two aspects. First, they are not anymore under the control of distributed systems experts. They are there, woven in the physical and social worlds. Distribution is not a technical means to an end to ensure availability or scalability. It's an inherent feature of the world. People, devices, data sources are inherently distributed. Likewise, concurrency is not a matter of speeding up computations, or it's not only a matter of speeding up computations or of timing issues. It's due to people and devices being inherently autonomously in time and space. The second kind of going out of order is that today's computations, today's applications, the order in those applications is not anymore, or is often not determined by the order of the program instructions, but actually driven by the external world, driven by the arrival of events and arrival of data, driven by data flow. So basically we end up with a mismatch, if you want, of orders. The instruction order doesn't confine to the data flow order. Data comes asynchronously when it comes. It's not determined by the order of the instructions. And we need to solve this mismatch. And in fact, the problem, if you want, you could say, okay, the problem is not new. We have had interrupts since computer science exists. But the problem is that interrupts used to be the exception from the normal, and now they are the new normal, so to say, not derivation from the normal. There is a lot of them. We need to aggregate. We need to drive computations based on their arrival and patterns on the arrival of data and events. So far, our answer to managing reactions to events and external happenings have been callbacks. But they are also well known for what is called the callback hell, meaning that they lead to complex and error-prone designs, easy to get inconsistent. Why is this like it is? There are two problems basically, which are related to each other. First, in order to manage reactions, we have the application developer kind of plays compiler. It's not the machine that manages the reactions, it's the application developer that has to do this by typically modeling callbacks attached to events, the implementation of callback interfaces and their registers are implemented as part of the application logic. The same holds for the management of the life cycle of callbacks, and for the consistency of the application state is the responsibility of the application developer. And B, what this ends up is boilerplate code and complex control flows, like kind of indicated in this picture, which are hard to reason about. And this is kind of amplifies the problem with keeping the state consistent. And you'd say, okay, the examples of the applications that I mentioned, they are there in the world, so they exist. So it doesn't seem to be that difficult to build them. Indeed, but we have to keep in mind that they circumvent many of the problems that I mentioned by employing basically centralized state management. Let's face it, our apps are basically essentially just thin interfaces to processing computations that are managed in central servers and clouds of platform providers. And the big tech companies, Amazons and Googles of this world, and Microsoft is pushing this trend further with serverless computing. Kind of even the business software is supposed now to move to their servers and clouds. But centralization is not a good fit for many aspects, like for offline availability, readability, low latency, efficient use of communication resources, and also for user-controlled data privacy. So there is this tendency now of going decentralized, especially in Europe with the new regulations about data privacy. This has become an urgent need to keep data decentralized, but also we see trends in machine learning going federated for example, for better use of communication resources, but also for privacy and reliability and low latency. So we need to replace this centralized state management with decentralized consistency management. To sum up that part, where we stand is that computing is big and out of control. Disorder is the norm, broken state is the norm, and this has been basically in essence like this since the 80s, if you want, But the open, dynamic, and interactive nature of today's distributed applications just amplifies the problems. And moreover, we can't now rely for this kind of application on skilled teams at big tech companies to get things right. Now, I mentioned that consensus is challenging, but I didn't say much. Why is it like this? We mentioned that there is a lot of complexity, that things get out of order, state is broken, disorder is the normal. And the traditional answer to this complexity has been consistency protocols that ensure strong consistency guarantees. So correctness of applications by design, if you want. And there have been several such coordinations and consensus protocols proposed. Some of them are some of the most beautiful algorithms that we have invented as computer scientists. Among those examples are Paxos, two-phase commit, global barriers, underlying computational models like bulk synchronous processing, and so on. They enable autonomous, loosely coupled machines to jointly decide how to control basic behaviors, including the order in which they access shared memory. Transactions are the weapon for order in the database management systems for coping with multi-threading and concurrency. And I will use them to illustrate how coordination protocols re-establish order, because we need to keep this in mind for the rest of the talk. So typically there is in essence always some underlying theory behind the consensus model. In case of transactions, this is serializability. And then based on this theory, engineering makes sure that an illusion of order is created and that this illusion is transparent in the sense that it doesn't show up in the application code, is provided to the application and application developers, so to say, out of the box or by design, which is a good thing. This is exactly what we want to do, because we don't want to have ordinary developers be concerned with managing consistency in such a dynamic world. But so this is very nice to have application correctness by design, but this solution, strong consistency to achieve correctness by design, has been challenged since a long time. At least since 2000, Eric Breuer formulated the so-called CAP conjecture, which was also proven later. So there is CAP theorem, which basically says that we cannot have all three here at the same time: consistency, availability, and partition tolerance. We have to sacrifice one, which basically says if we have strong consistency, we cannot have partitions or availability. And there have been a lot of work from the theory of distributed systems community showing, for example, that fast transactions are impossible when we have partitions, when the connections break. So we need to do something. In the applications that we are looking at, interactive distributed applications, partitions are given. And availability, since they are interactive, is very important. So we need to do something about consistency. And this is kind of has been put very nicely in this quote from a talk by James Hamilton, who is the VP responsible for Amazon services. And he says the first principle of successful scalability, availability, is to better consistency mechanisms down to a minimum. Put them off the critical path and hide them, and make it very hard for application developers to get permission to use them, because it's hard for them to use them in the right way. So what followed as the answer was the NoSQL era, with a lot of systems that basically drop strong consistency and instead replace it with maxims like use of commutative methods, inverse methods, compensation, and so on and so forth. And in terms of practical engineering, what this brings is easy to scale infrastructures, but tricky or challenging to ensure application correctness. This is not, I mean, when this started, this was not a big issue because we had the same teams at Google and Amazon and Microsoft developing the infrastructure and the applications, and these are smart people, kind of skilled people, let's put it this way, and we can't get skilled people at scale. And if we want to democratize the development of massively collaborative and interactive applications and do so in a decentralized manner, we need to offer correctness guarantees out of the box, but in affordable ways in terms of performance. And even Eric Breuer, who formulated the CAP conjecture in the first place, reflected back in 2012, I believe, 12 years later, and said that, look, we have to choose between consistency and availability, but you don't have to take this for God-given. There is incredible range of flexibility for handling partitions and recovering from them. And he reformulates and says the CAP goal should be to maximize combinations of consistency and availability that make sense for the specific application. So the flexibility that he hints at, I believe, is that different applications may need more or less coordination. So sometimes consensus or coordination is not needed, but it's kind of a result of a design decision. We can coordinate, get consensus in traffic also this way without traffic lights, right? The decision to get consensus via traffic lights is kind of a design decision that we have taken. This problem is kind of solvable also without traffic lights, without these strong barriers. And then there are areas like in data centers, partitions are very rare, are under control. So in this scenario, you can have availability and strong consistency at the same time. And then there are other scenarios, critical applications where you just cannot drop strong consistency. You need to ensure correctness by design. So this is a very kind of constructive reconsideration of CAP. We need to maximize combinations of consistency and availability. We need to do trade-offs. The question is, who does this? And in his answer, Breuer basically says the application developer, since these combinations are specific for specific applications, the only persons that know about application semantics are application developers. And this is kind of tricky. We want to relieve them from very challenging decisions about combining consistency and availability. So given this flexibility, the question is how to automatically maximize combinations of consistency and availability, or the consensus and availability, and how to create affordable illusions of simplicity despite the complexity of the matter. And I pretty much love this picture that I have borrowed from the book by Grady Booch on OO design. It's a very old book. I started studying this book when I started my PhD. And he says the task of software development teams is to engineer the illusion of simplicity. What the point I want to make is that the task of programming technology providers, of language designers in this case, is to engineer the illusion of simplicity for software developers. And there is quite some work going on targeting this goal from different communities, from the distributed systems community, database community, and programming language community. And I have very roughly characterized here 3 different areas, like There is some work going on theory of asynchronous problems, asking the question or trying to characterize the class of problems that can be computed without consensus in a distributed way. And Rashid Garawi and his team, for example, had 2 recent papers proving that the double spending problem in blockchains, in Bitcoin blockchains, can be solved without consensus. So we use their very heavy consensus mechanisms, but they seem to be an incident of wrong design decisions. Another proof that they have delivered is that machine learning or the learning problem is also an asynchronous problem, meaning a problem that can be solved in a distributed way without consensus. There is a lot of work going on, I mean, since at least in the last 10 years, but still going on designing replicated data types that, replicated data types that are either easy to merge without conflict, without any consensus, or that can be merged with minimized consensus, but with proven correctness guarantees. So I call them building blocks to develop applications that kind of maximize these combinations of consistency and availability. And then there are works in the area of formal reasoning, formal methods, on correctness of solutions that maximize combinations of consistency and availability. And I believe that there is a key role that language design research has to play to glue these things together, to enable automation, to provide developers with abstractions that they can use to manifest enough application semantics, to enable the language machinery to automate the reasoning and to make decisions about combining consistency and availability. And this is what I will talk about in the second half of my talk. I will present one particular language-based approach. This is Rescala, a language that we have been developing in the last maybe 8 years, which is a reactive language, and I will explain what it means to be a reactive language. So I will start with introducing some basics of reactive flows. Then I will talk about serializing them in a multi-threading setting, making them partition tolerant, and then I'll talk about hybrid flows, kind of applications that combine both strong consistency and weaker consistency models, availability models. But let's start with the basics of reactive flows. So you remember this picture with the spaghetti control flow on the left, and the logic that is expressed there, I mean, we didn't look at it, but it's as simple as you see here. Only if we had the right programming abstractions, namely reactive evaluation semantics. Reactive evaluation semantics is kind of on par with other evaluation semantics that we know pretty well, like lazy evaluation, eager evaluation. This is a different way of evaluating computations. You don't call a function when you have new parameters. When parameters change, the function gets executed automatically. So basically, in Rescala, you have two kinds of reactive abstractions. Signals. These are time-changing values. What I said, these are computations that change automatically with time when other computations or data inputs, they depend on change. So, and these signals, they can be arbitrarily composed with each other, and we even have predefined combinators for doing so, things like fold and map and filter and zip. And Rescala also, another kind of reactive abstractions are events, and signals are composable. So the key point is that changes are automatically and consistently propagated to dependent computations. So keep in mind, I will explain what consistently means. So a Rescala program basically reminds or is reminiscent of an Excel sheet. When you change a cell, everything else that depends on this cell is automatically brought up to date. Nothing you need to do. The Excel machinery does it for you. The same thing here with Scala. You change some data, you change some computations, anything that depends on this data and computations is brought up to date automatically. The language machinery keeps track of reactions to change. To give you a flavor, let's assume we a glimpse of, an intuition of the language. Assume we want to implement a to-do list, and you don't need to look at the details of the code, Scala code. But what's important is that you see here, I create a value, which is an event. Another one is also event. This one is used for creating a task. So there is a data flow or dependency flow from this value to this value. There is a dependency flow from here to the task list. Task list also depends on create task and also on task data. So at the end, the Scala compiler, given a Scala compiler, given a Scala program, automatically translate the program into a dependency graph. I mean, the dependencies are very explicit in the program if you want. So internally, the reactive programming machinery looks like this. You have this dependency graph. These triangles are source reactives, so these are inputs to the whole computation, and circles depict derived computations, so those that depend from other computations. The graph manages, if you want, stores and manages and invokes all signal computations, the user-defined computations, here on the left, and the input that comes from the surrounding worlds, new data, new events, and so on, they are managed by the propagation algorithm, which, given the inputs, starts re-evaluating computations in the graph and re-evaluating, of course, only nodes in the graph that are affected, that are in the transitive closure of the inputs that changed. And in turn, the graph invokes the user-defined computation. So there is no way, so to say, to talk to the user-defined computations from the outside world directly. There is always this intermediary of the propagation algorithm, which is hidden from the application code. I mentioned that the propagation of updates is consistent. We also say glitch-free to indicate that they are instantaneous. I mean, they happen as if they were an atomic operation. So starting with a consistent state of the application, when I do an update, all changes in the update happen in one instant and move the state from one consistent resting state to another consistent resting state, and so on. Now I have another update, and you see here that there are two paths that go from the input to this node in the graph. Nevertheless, we never see two different values. So each computation has an write once semantics. I mean, the nodes are executed only once. The node here waits, every node waits for all inputs to have re-evaluated before it re-evaluates. And that's what brings this instant property of the updates. So we move, the whole graph moves from one consistent state to another. Okay, to wrap up, these were the basics, if you want. The take-home message is basically that we go from a world where we programmatically, in the application code, track dependencies between computations, to a world where automated flows of signals and events go through dependent computations. And we have done also some empirical studies showing that this paradigm shift, if you want, helps with comprehension And the key thing is that it does not only help developers to better and easier reason about programs, it also helps the language machinery, as I will show in a minute, to so that the dependency graph, if you want, manifests valuable application level semantics to the language machinery so that the later can use this information to automatically ensure correctness in the presence of disorder due to concurrency. So these flows can be concurrent, and once they run concurrently, we may have clashes. They can share nodes in the dependency graph, and then it's a question, what's the result of the application of the parallel or concurrent flows? We need to coordinate that. We need to bring order. And our idea, given that we have this information about the dependencies between computations, and we know how the execution progresses basically in the topological order of the graph, we basically consider updates, if you want, as if they were transactions. So we need to split this concurrent. Even if they are concurrent, we need to make sure that they run as if they were executed one after the other. And that's what we actually achieve. We have formally proven that our scheduler, our change propagation algorithm, ensures abort-free strict serializability, very strong consistency property. And I will come in a minute to show that this happens syntactically and semantically in a transparent way. Let's see what that means. But also here it's important to see abort-free. So we know we can ensure that the updates, we don't need to abort updates. They don't clash. There are no changes that we need to take back. And this is a very strong property, which I would say I will explain is due to the language properties. Because this is very hard to ensure, for example, with traditional transactional systems. And syntactically mean without the need to change application code. So transactions do not show on the application code. We can take an existing rescaler program, run it on top of the thread-safe update propagation, and it will run in a thread-safe way. And semantically transparent, what I mean is this property, abort-free strict serializability, is very strong. So there is no change in the behavior of the application. No aborts happen. If they happen, you notice that it's not the equivalent behavior of an application that is running in an environment that doesn't have multi-threading. So that's what is meant by semantically transparency. Semantically transparent, what it means is that basically the API, all the abstractions, the reactive abstractions, like the declaration of a new signal, reading the value of a new signal, setting the value of some variable, all this, or firing an event, all these operations are basically implicitly considered as if there were transactions in our transactional world. And this is done by having basically transactions be defined in terms of operation on the dependency graph, not on application level state reads and writes. So the thread safe, the propagation algorithm becomes thread safe, the rest remains the same. I basically said what it means to be semantically transparent. I want to say only 2 words about how we achieve this. We basically borrow ideas from multi-version concurrency control from the database area, database community. So each transaction basically creates its own version of the state. And before starting executing, each transaction puts an empty placeholder version on the node. So each node has a list of placeholders of versions associated with it. Each transaction, the colors here like orange or green stand for transactions. Each transaction has its own version in the beginning before starting running. They kind of put placeholders in all nodes that will be affected by the transaction, and this is key here. Each transaction knows exactly from the very beginning which part of the graph it will affect, because it knows which inputs it is changing, and basically the graph affected, the subgraph affected, is the transitive closure from those input nodes. So they reserve a place where to put their value, and then they start executing and do so in a pipelined way, so concurrently, but coordinated. There is this transaction order that is established while transactions put their placeholders in the lists of versions on the nodes. So, and during propagation, then each of the instance or each of the transactions basically fills those holes with real value. Okay, so to wrap up this part, I showed you that given these reactive flows, we are able, due to the language abstractions, and I will come in a minute, to ensure order in face of multi-threading, and do so in a syntactic and semantic transparent way. And also, so basically we create illusions which are transparent and they are affordable. I didn't talk about performance, but there is more about this on the paper. I just want to emphasize the thing that this is due to the declarative programming model. We have explicit data dependencies. We have topological order of evaluations. We have this write once semantics. Each node is written during a propagation only once. And we have the application state, this user-defined computations encapsulated in reactive abstractions. These are the 4 key properties that enable us to create these transparent illusions. Explicit data dependencies help with determining, if you want, the execution plan of a transaction ahead of time. And this is what avoids deadlocks and hence aborts. And the topological order of evaluations helps doing this even if the dependency graph changes on the fly. So our graphs can change dynamically. If some node is if then else, then this can have changed the graph itself. The write once semantics enables us to run transactions in a pipeline mode. As soon as a transaction has filled the placeholder at some node, it is given free, it's visible to the other transactions, they can continue using this value. And then the application state encapsulated is what gives us the syntactic transparency. So the other tiles that are colored stand for semantic transparency, and this one for semantic transparency. And we have shown, I will go fast, that this can extend to distributed serializable flows. The same algorithm extended. Of course, when we go distributed, now in order to keep this very strong consistency guarantee, we will need coordination, but we reduce the amount, the need for coordination to only this transaction graph management. So the order in which the transactions are executed is kept in a transaction graph, and there is this algorithm of transaction graph testing that makes sure that the graph stays, for example, a cycle. And this is the only place in the system where we need coordination. So we have reduced coordination to a minimum hidden from the application developers due to syntactic transparency. Nevertheless, this part, the small part where we have strong consistency, it doesn't tolerate partitions. To get consensus, you have to be all online, if you want, at the same time, which may be unacceptable for our interactive applications. And moreover, I want to recall that I said there are problems that do not need consensus. For them, even this minimized consensus is too much of a consensus. And so for these scenarios, so when we want to have availability, when we weight availability more than consistency, and for asynchronous problems, we need a failure-tolerant distributed update or propagation or failure-tolerant flows. And when I say failure-tolerant, I mean two kinds of failures, network partition, but also crashed or Byzantine devices, any number of them, of the distributed hosts. How do we solve this? We basically make use of conflict-free data types. In our case, we call them conflict-free replicated data types. So in this slide, just the only thing you need to notice is that now we have kind of replicated to-do lists. And the only difference in code is basically that now we use these new kinds of data types like replicated list or this kind of last writer wins. These are basically so-called conflict-free replicated data types. There are tons of papers about conflict-free replicated data types. In essence, they are basically data types which have a state domain that is a join semilattice. So given the join operator that has certain properties, is associative, commutative, idempotent, we ensure that if two replicas diverge, change in different ways, we can nevertheless merge their diverged states automatically by the join operation, thanks to the commutativity of the join operation or associativity. And the simplest example of such a data type is a set with union as the join operator. You can, this builds a lattice. The distributed property of the join is here added by John Hellerstein. It's just for fun, just to get to ACID, because you want to make this point ACID 2.0, kind of to allude to the ACID property of databases. Now, you might ask, how many data types can I implement as conflict-free replicated data types? And it's tons of them. So here you see a list, and there is more. There are libraries with CRDTs. There are even databases that are based on CRDTs, and there are languages for composing CRDTs like LASP and BLUE. And there are there is new research or more recent research going on. For example, this paper on mergeable replicated data types that try to get any data type that can be special, can be expressed, can be specified as can have invertible relational specification, and then map these specifications automatically to conflict-free replicated data types implementations. This is it I want to say about them. How we use them is basically at the distribution points. If you know, when two hosts communicate with each other, the setting is now we have several hosts, several devices, and we have the dependency graph, and these nodes in the middle are replicated. And then changes can happen at different devices autonomously, but when they have connectivity, they kind of broadcast their changes to other devices, and eventually all devices have the same state. They are merged in a conflict-free way, means without consensus. So eventually they reach a consistent state. And the property that CRDTs guarantee is strong eventual consistency. So it happens eventually. It's not guaranteed that it will happen, but as soon as there is connectivity, we get strong consistency back. Now, this is the property of individual reactives that are replicated. What does it mean for the entire state of our application? And I show this by using transactions, because I said our updates are seen as transactions that move the state of the overall graph. Move the overall graph from one state to another. Now, in this figure, the time is moving from left to right. We have two devices, one on top and one in the bottom. And devices move from one state to another, so that their state transitions. The different states are represented in device 1 as rectangles and in device 2 as circles. And moving from one state to another is depicted here by coloring the boxes in pink, and here by coloring the periphery, so to say, with yellow. So the first device, transaction A executes, we move to state A. Transaction C execute, we move to state AC, and eventually, and device B moves with the transaction B to state B, with the transaction D to state BD. Now these broken lines, they are basically connections. This is where connections happen, where there is connectivity. And at this moment, device 1 broadcasts its state, it was A, to device 2, which in this position merges it together with its own state BD. The same thing, device 2 gets connectivity and broadcasts its state when it is at BD and reaches A in its state AC, so we get to A, B, C, D, and finally the two are merged into a next consistent state. Now, if you look at this picture, this is basically a lattice again, right? And so the message is here that our instant flows or transactions move the state of the devices autonomously from one state to a bigger state, to a higher state in the lattice, and eventually they are merged together. Now the question is, how do I go from a program with separate CRDTs, with several CRDTs, to this overall state of the application being itself a lattice? And that's where the graph comes into place. Because the program is mapped to this dependency graph, and the composition of different reactives that ensures that we get a lattice at the end is due to transactions that basically move the entire graph from one consistent state to the next one, as I mentioned. Okay, let me close this part by saying that what we get at the end is end-to-end, or I mean by this an application-wide strong eventual consistency. States may diverge at the data center from devices or from one device to another, but they are exchanged, they are broadcasted and eventually merged to get to the next consistent state. And if one device crashes, we do have a kind of a snapshotting and recovering mechanism in place, which fits very well also with this reactive programming approach. Once the state is recovered, is propagated just as if it was a new input. Now, here we are, we have two kinds of propagation algorithms. One that is consensus-free, is partition tolerant, but only ensures causal consistency, respectively strong eventual consistency. A weaker consistency guarantee than the previous one, the algorithm that ensured strong consistency with minimal synchronization, but yet enough synchronization to be partition intolerant. Now, since we have them integrated uniformly into the same programming model, they can use together within one application, but the decision as what to use in which part of the application remains part of the application design. And you remember that I wanted to take the responsibility of making decisions about combinations of consistency and availability away from developers, so we are not yet there, and we are working on this. This is some work that is going on now, where we basically, instead of having only the input program, we add to the programming model some behavioral specifications, so pre and post conditions for transactions and safety invariants for the whole application. And given these inputs, there is some verification machinery going on that automatically derives transactions or finds which transactions need synchronization. And then we need to have strong consistency only at this so-called synchronization points. But I don't have time to go into more details about this and would like to summarize at this point. So I've started by saying that today's applications are massively distributed and out of control, that consensus is necessary to re-establish illusion of order, but needs to be used with care. I concluded that first part by saying that we are in need, we are looking for new affordable illusions that maximize the combination of consistency and availability, and that the need is being addressed from different angles across communities, and then that PL-based automation is needed to glue different angles together and to relieve developers. And in the second part, I presented one such PL-based approach that we have developed with my team. And I said it several times, our weapon to achieve automation, to automatically maximize the combination of consistency and availability in a transparent way, are reactive programming features and recently also application level behavioral specifications. Having said that, let me conclude the talk by giving credits to my team, to the Rescala team, by saying thanks to ERC, the European Research Council, and also the German Science Foundation, DFG, who have funded this project or projects. There are several projects. And yeah, let me give you some links to the Rescala language webpage and also the project, although this one is a little bit outdated today. And let me thank you for your attention, and I'm happy to take questions now.
Thank you very much. Thank you very much for the interesting talk. So I think you're supposed to write your questions in the chat. I cannot see any.
Should I end the presentation? Maybe it's all right.
You mean the slides? You can keep them to be like.
Okay.
Someone was saying something. I heard. Was it Farhad or? No. Okay, I have a question. This. Okay, I have a question from the chat. Are there any case studies for the language? Vladimir is asking.
Excuse me, I didn't. I'm trying to get to the chat show conversation, right? No.
Are there any case studies for the language?
Oh, case studies. Yes, they are. So, I mean, not big ones, not industrial level use cases, but we have a lot of them on the webpage of Rescala.
Okay. So we have this language of reactive object languages since 2001. It's not an executable language, but I'm wondering, so your modules, they are actors, right? That's Rescala. So it's just
you can call them actors. So we hide actors behind. You can implement this thing on top of actors, but we avoid this explicit message passing, right? So you just write computations with their dependencies as they happen, And then you can map this down to actors.
Okay. So actors are going to do that, right? At the end. That's what you're saying?
Yeah, you can use actors as an implementation basis behind the scenes.
Okay. And so the message passing will be there underneath.
Yes. I mean, you can use, I mean, Riscala is very flexible, the architecture, in the sense that you can use different communication technology underneath. And we, in the theoretical, in the proofs, we make very little assumptions about the capabilities of the communication infrastructure in terms of reliability and such, because we ensure this at the language level, if you want.
Okay. So, and you mentioned this callback hell. So you are just hiding it. Can you explain a bit?
Of course. So basically, I said with the callbacks, we are letting the developer to play compiler. Reactive programming, I mean, you can implement reactive abstractions by callbacks in behind. But I don't want to, I want to think about it as just a third alternative to application semantics. So we have eager evaluation or evaluation semantics. We have eager evaluation. We evaluate the parameters to a function before calling the function. We have lazy evaluation where we don't evaluate parameters. We just keep them, their expressions, as we go, and then evaluate them only when they are needed. So it's call by need. And this is kind of call by reaction. You evaluate anytime something changes. And of course, one way to implement this is by using callbacks behind the scenes.
Okay. And you had one condition which you said is a strong one. Now I can't remember exactly what you said, but it was something that you don't need to roll back, or yeah, that was the condition.
Yeah, we don't need to roll back because due to, so the machinery, the language machinery, the propagation algorithm has this graph, manages the state of the application in the dependency graph. When a transaction starts, we know exactly which nodes in this graph will change eventually during the execution of the transaction. So every transaction can put a mark in those nodes, kind of saying, I will be running here, right? So at this point, we order these placeholders. When there are two transactions meeting at one node, we fix the order in which they will execute and propagate this order consistently in the following nodes. So at this preparation phase, we have ordered transactions already so that when they run, they cannot have deadlocks. So there is no need to abort any of them.
Okay, thank you.
I see some more questions. Yeah,
questions are coming up. Mike is asking, can one always reach consistent states in presence of loss of connection of devices?
I mean, if a device disappears forever, of course not. So the rest can achieve consistency. But as I said, we have this snapshotting and recovery mechanism, which I didn't talk about. So once in a while, every time we reach a consistent state, we store a snapshot. I mean, this is what we do now. You can do it more rarely, depending on trade-offs between consistency and efficiency. And the good thing is the reactive programming abstractions help us there to store a minimal amount of state. We only need to store the inputs and faults. I didn't talk much about them, stateful reactions. All the rest is derived, can be recomputed when the device is again back. We get the snapshot, we restore the state, and then the restoring the state means basically refreshing the inputs and the faults, and the rest is propagated. We just do a propagation as if there were new values there. And this propagation goes on across device boundaries. So yeah, if a device doesn't disappear forever, then its states will be propagated.
Okay, and the next one, Jose is asking, he's saying, thank you for the great talk. I have seen there is also a Scala Loki developed by your group. Do you know how it relates to ReScala?
Yeah, of course I know. So Pascal in this slide is the kind of the main developer of Scala Loki. Scala Loki is a multi-tier language. So the idea is when you have, we avoid there having to implement, let's say, client-server architectures by having a client program and a server-side program. And there are a lot of things that go wrong if you do it like this, which is the norm today. In Scala Loki, you write the program as if it was one piece, and you have placements, placement concepts to place computations in different hosts in an distributed architecture. And basically, ReScala uses this replicated reactives. They have a name. They are bound to a name which is known across devices. And there, for example, we use the type-safe distributed naming of Scala Loki. So we built on top of part of the Scala Loki infrastructure and also make use of this flexibility to exchange the communication infrastructure. The next step, we would like to make the placements also dynamic, but this is a different story.
Okay, thank you very much.